Transverse electric analysis of the rectangular metal waveguide. Just like the previous video, this video is going to have 4 parts. In the first part, we're going to perform the TE analysis of the metal rectangular waveguide. Given that solution, we'll talk about that solution, we'll analyze it, figure out what it means, then visualize some of the modes and conclude the video. TE analysis.
So for TE analysis, we have our governing equation just like we did for the parallel plate. Since we're doing TE analysis, that means that the Z component of the electric field is 0. So our differential equation is solving for the Z component of H. And we had a Laplacian in this equation that we've expanded into Cartesian coordinates. Once we solve this, and we have an expression for H, well, then we can substitute it back into these equations to calculate all of the other field components. So first, we will write the general form of the solution. So we're solving for the Z component of H, and so we have the product of 2 terms. We have this amplitude term, which is a picture of the mode in the cross section, so it's only a function of x and y. And then we have the e to the minus j beta z. That's what's responsible for accumulating phase in the z direction, the oscillations in the z direction. Now here's where, when we look at this rectangular waveguide, we're looking at it as if it's 2 parallel plate waveguides. That analogy, I think, will make this a lot easier. So if we weren't drawing that picture, or we were just a mathematician, we would say that we're going to solve this by separation of variables. That means this amplitude term we're going to write as the product of 2 one-dimensional functions. Capital X here is the one that varies only along x, and capital Y will be the one that varies only along the y direction. And so this x will very much be like our horizontal parallel plate, and the y will be very much like our vertical parallel plate. So let's go ahead and apply separation of variables. So we start with our governing differential equation. We recognize that we're going to write our unknown function, the h naught z. We'll write that as the product of 2 one-dimensional functions. So we will then substitute that into our differential equation, and we end up here. Now notice I dropped this parenthesis x, parenthesis y notation. Technically they should be here, but just for simplicity I've dropped them. So we've written our differential equation again, but now having substituted h for x times y. Now we notice in this first derivative that y is not a function at all of x. It is able to come to the outside. And we brought it to the outside down here. Likewise, in our second derivative, x is not a function of y, and so we bring it to the outside. Then last, our partial derivatives are written as ordinary derivatives. Because if we look up here, we have a partial derivative with respect to x of a function that is only a function of x. So the partial becomes an ordinary derivative. And I can say the same thing about this second partial derivative. It's a partial derivative with respect to y, but capital Y is only a function of y. So the partial derivative is written as an ordinary derivative. So here's a new differential equation for us to solve. Let's first focus on the x dependence in this differential equation. So we're focusing on this term, which really means the rest of this stuff inside the differential equation is just a constant. To make this look like a wave equation, let's take this group of constants and let's just call it minus kx squared. And the reason we give it a minus kx squared is so that when we replace this with a minus kx squared, our differential equation is the wave equation. It's the wave equation in the x direction. Now let's take the same differential equation. I juggled terms around a little bit. I brought the minus kc over here. Let's focus on the y dependence. So all of the y dependent stuff is right here. And that means the rest of these terms are a constant in this equation. So let's replace that with a minus ky squared. That makes our differential equation a wave equation that's only a function of y. So we've converted our single differential equation, which is a function of x and y, really into two one-dimensional wave equations. One's only a function of x, the other's only a function of y. That is the separation of variables. We will solve these separately and then bring the solutions together. Let's do something to see if what we've done up to this point is correct. If these two one-dimensional wave equations really do represent our original single differential equation, we should be able to add them together and recover the original differential equation. So the first thing I'll do is I'll rewrite those equations, but the first equation I divide by big X, and in the second equation I divide by big Y. So there's no big X to the right of kx. Now we're dividing by 1 over big X here. We're dividing by 1 over big Y. So same equations, we've just divided by big X and big Y. Let's go ahead and add these two together, and we end up with a new equation. Now let's compare this to our original differential equation. So in blue at the bottom right, this is our original differential equation, and what we can see is that these two really are the same thing if we define kx squared plus ky squared as kc squared. So we can easily do that, and we do recover our original differential equation from both of these. So another sort of justification of this separation of variables. So we have two differential equations to solve. We've actually already solved these. We solved these when we looked at the parallel plate waveguide. So we know their solutions. We know it's a cosine plus a sine. And we can just go ahead and write that immediately. They have different constants. So our solution in x will have an a and a b, and y will have two other constants, but we can't call this a and b because these are different constants. So we have to call them c and d. Otherwise, it's the same solution we did for parallel plates. Now that we have a solution for x and y, we can bring them together. Remember, we originally wrote our solution for h naught z as the product of x and y. So if we multiply together these two general solutions, we now finally have the overall general solution for h naught z solved by separation of variables. Now to solve for those constants a, b, c, and d, we're going to apply the boundary conditions. We have an electric conductor around the outside of this waveguide. So for an electric conductor, that forces the tangential components of the electric field to 0 at the interface immediately up against the metals. Well, the problem is we've just found the magnetic field. Our boundary condition is a boundary condition for the electric fields. So what we'll have to do is we'll have to take our solution for h naught z and then use that to come up with general expressions for E naught x and E naught y. So we can do that. We have these expressions to calculate all the other field components from h naught z, and so that's what's done here. And so we come up with a general expression for the solution E naught x and the general solution for E naught y. So it's these two equations then that we will apply our boundary conditions to figure out what is A, B, C, and D. So let's apply the boundary condition at the x equals 0 boundary. We apply this to E naught y, and we're going to set x equal to 0. So we're setting x equal to 0. Of course, sine of 0 is 0, so this term disappears. Cosine of 0 is 1, so we're really just left with b. Now for this whole expression to equal 0, that means that b has to equal 0. So we found b, and we can drop that term off of the general solution. Now we'll do the boundary condition at the far right-hand side of our rectangular waveguide. So that's where x equals a. So we're applying this still to e naught y, and we set x equal to a. So here x is equal to a. Notice the other term is gone because we've already found that b equals 0. So the second term in the square brackets is not there. So for this entire expression to equal 0, well, we could set a equal to 0, but similar to what happened with the parallel plate waveguide, we'll recognize if we set a to 0, the entire general solution goes to 0, and that makes no sense. We don't have a physical answer there. So that's not an option. So something else must be forcing this to 0, and it turns out it's the sine term. So we have to set that sine term to 0. Now when we do that, we recognize that this sine will equal 0 anytime its argument is an integer multiple of pi. And so any integer multiple pi will work. And that's the origin of having multiple discrete modes in this waveguide. Now our integer m could be 0, 1, 2, 3, or whatever. And remember with parallel plates, we weren't quite sure if the m equals 0 solution's valid or not. This is something we will look at later. For right now, we'll just pretend that it's a valid solution, but we'll come back and figure out what conditions that can be 0, maybe or maybe not. Now we move on to the boundary conditions at the top and the bottom of the rectangular waveguide. So let's look at the bottom, y equals 0. We apply this boundary condition to E naught x because this is the electric field component that's tangential to the top and bottom plates. And we set y equal to 0. So over here we're setting y equal to 0. Of course sine 0 is equal to 0, so this whole term drops. Cosine of 0 is 1. We're just left with d. And of course to make this entire expression 0, d has to be 0. Now let's look at the boundary condition at the top of the rectangular waveguide. That's at y equals b. So we're still applying this to E naught x. We set y equal to b. Over here, we have a minus c sine kyb. The d term that was over here is gone because we found that d equals 0. Now if we set c equal to 0, then our entire solution is 0, and that's not physical. That can't be. Therefore, it has to be the sine term that's making this entire expression 0. So if we set the sine term to 0, its argument could be any integer multiple of pi. So kyb has to be any integer multiple of pi. Now here I'm using n to be the integer instead of m like on the previous slide. And for now, we will let n be 0, 1, 2, 3, and we'll figure out if 0 is valid or not. We'll pick that up later. So this is an origin of multiple modes again. And now we actually have two integers to think about, m and n. So here's our revised solution now for h naught z. We found that b and d are both 0. That means the general expression for h naught z just becomes this, looking pretty simple. And our two constants, a and c, we were never able to find. However, a times c, if those are just two unknown constants, becomes just one unknown constant. So we're going to write this as a sub mn. And that's going to remind us this is the amplitude of the mode number that we're indicating with a choice of both m and n. So we will call this the 0-1 mode or 1-1 mode, etc. So that's our general expression for h naught z after applying the boundary conditions. So remember what kx and ky were. We had kx being m pi over a. We had ky being n pi over b. And so we can write our general expression for h naught z a little bit differently that doesn't have kx and ky in it. Now if we take that general expression plug it back into our original equations where we calculate all of the other field components from H naught Z, we end up here. And of course, really the last final thing to do is, for the field solution, for the overall fields, we need to tack on the e to the minus j beta z. Notice what we've done with beta here, beta sub mn. Each mode has its own phase constant. So we just give it the subscript mn so we can assign each mode its own phase constant. And its own amplitude term, amn. Now if we take that general expression, plug it back into our original equations where we calculate all of the other field components from H naught Z, we end up here.
Analysis of the TE solution.
Now let's think about the phase constant. Remember from separation of variables, this Kc we found had to be Kx squared plus Ky squared to make the separations of variables valid. Well, we know now that Kx is m pi over a and Ky is n pi over b, so now we have an expression for Kc squared in terms of these integers m and n and the dimensions of the waveguide a and b. From this, we get our phase constant. So the original definition of this cutoff wave number was k squared minus beta squared, so we'll solve it for beta squared. K squared minus Kc squared. We have an expression for Kc, and now we have an overall expression for our phase constant in terms of m, n, a, and b, and of course, little k. So clearly, each mode, indicated by m and n, has its own phase constant. Now on to the cutoff frequency. So we'll back up to where we're using the cutoff wave number in our definition of our phase constant. We have the square root of two numbers. And this is, the phase constant should be real. That means the argument inside the square root has to be positive. If this goes negative, we will get an imaginary beta, and that does not make any sense. That actually corresponds to a cutoff mode. So we need k squared greater than kc squared to be talking about a guided mode, and this is why we call the Kc our cutoff wave number and why it actually controls what is our cutoff frequency. So we need K greater than Kc, and so from this we can calculate a cutoff frequency just like we did for the parallel plate waveguides. So we need K greater than Kc. We know that K is omega times square root of mu epsilon, so here's our frequency term that appears. We can convert our angular frequency to an ordinary frequency, and I put a sub c here to remind us that we're calculating a cutoff frequency from Kc. And so now we can replace Kc with the m pi over a squared, m pi over b squared, square root of that, and we have a nice equation now for calculating the cutoff frequencies for our TE modes. Characteristic impedance. So the characteristic impedance is the amplitude of E divided by the amplitude of H, and we have expressions for those now. So we can work through the math and simplify, and we have an expression now for the characteristic impedance. And we also have an expression for our phase constant, so we are actually able to calculate the impedance of our TE modes. Let's think about the cutoff for the first order TE mode. And remember, this is the frequency. Below this, our waveguide is completely useless. So we write our equation for the cutoff frequency. And let's think about this. What about the TE00 mode? Let's plug in 00 for M and N. Well, if we do that, we get a cutoff frequency of 0. That doesn't make any sense. We know that this is not a transmission line. It has to have a cutoff frequency. So what we conclude is that when M and N are both 0, that is not a valid mode. So the TE00 mode does not exist. What about the TE01 mode? Well, if we plug in 0 for M and 1 for N, we actually get an answer for the cutoff frequency. So this is a physical mode. What about the TE10 mode? So we plug in 1 for M, 0 for N, and we get another cutoff frequency. So this is a physical mode and it exists. Now the question is, which one is the lower frequency? Well, both of these equations have a 2. They both have a mu epsilon. So it's really the 1 over B and the 1 over A that's going to determine which one is the smaller or lower cutoff frequency. So in our convention, and we're having a rectangular waveguide, we do this such that A is always greater than B. So if A is greater than B, then A is going to be the bigger number. So dividing by A will lead to the smaller number. That makes the TE10 mode the lowest order of the TE modes. And I'll add that we can't yet conclude that this is the fundamental mode of the waveguide simply because we haven't looked at the TM modes. It might be that the lowest order TM mode has a lower cutoff frequency than the lowest order TE mode. We don't know that yet because we have not analyzed the TM modes. But among the TE modes, the TE10 is the lowest order. Now, if for some reason you were violating convention and you made B greater than A, then it would be the TE01 mode that is the lowest order. But we don't do that. Our convention is that A is always greater than B. Let's think about single mode operation. Over what range of frequencies would a rectangular waveguide support only that first order TE mode? So we know that first order TE mode has a low frequency cutoff. We'll have to operate above it. But at some frequency, if we keep going high enough, suddenly a second order mode will come alive, and then it's now multi-moded. We would have 2 possible modes. So for what range of frequencies is this single moded? And we very often want to do this. Remember, the different modes are traveling at different speeds, and that can mess up our signals. So normally we want to operate a waveguide as single mode. All right, so the low frequency cutoff. We know the low frequency cutoff. It's the TE10 mode. But what about the cutoff of the next order mode? We actually don't know what the second order mode is. So is it the TE01? Is it the TE11? Is it the TE20? We have to consider all that. But those are the possibilities for the next lowest order mode above the TE10. So I derived expressions for all 3. And if we stare at this long enough, we can actually figure out which of those is the next lowest order mode above the TE10. So right away, we can conclude that the TE11 is always going to have a higher cutoff frequency than TE01, and that's simply because the bigger these indices, the higher the cutoff frequency. And so they share the 1 in the second place, but the TE01 has a 0, so it has to be a lower frequency. So right away, we can eliminate TE11, but now, which is a lower frequency, the TE01 or the TE20? And it actually turns out it depends on the relation of A and B. And it turns out that if our dimension A is less than twice of B, then it's the TE01 that will be the low frequency cutoff. If this dimension A is greater than 2B, then it's the TE20. And this honestly is the typical cutoff. If you've ever looked at pictures of rectangular waveguides, if you go and Google that, you will notice they are very rectangular. And so that is the usual case. And so the TE20 is almost always the next order mode that would pop into existence. But just remember, if A and B are a little closer, then it's actually the TE01 mode that would be the next. So what's the bandwidth of our rectangular waveguide? So let's go with the usual case where A is greater than twice of B. Now we have our upper and lower cutoff frequencies. And so our bandwidth is the difference of those. And our bandwidth reduces to this nice simple equation. Now, I want to introduce another concept, something called fractional bandwidth. And here is why that's meaningful. Let's say I have a waveguide design and I get some bandwidth. Let's say the bandwidth is 1 gigahertz. If I take that waveguide and I shrink all physical dimensions by 2, so it's half the size in all ways, it turns out the bandwidth will double. And that's because it's operating at a higher frequency now. However, it's really the same waveguide, just scaled. So we would like some measure of bandwidth that doesn't change as you scale the size of the waveguide. And it turns out we have that, and it's called the fractional bandwidth. So the fractional bandwidth is the bandwidth normalized by dividing by the center frequency. And if we do that for these two frequencies up above, it turns out we actually get a number, 66.7%. So as long as that A is greater than 2 times B, really no matter what our choice is of A above that, our bandwidth is always 67%. Fractional bandwidth is 67%. And no matter how we scale that guide, that 67% is always the same. So fractional bandwidth, to me, is the more meaningful way to measure the bandwidth of a waveguide. Let's do an example. Let's say we have an air-filled rectangular waveguide. That is the most common case, although we could fill it with a dielectric, but let's use air. And let's say that A, the width of the rectangular waveguide, is 3 centimeters, and B is 2 centimeters. So first question is, what is the cutoff frequency of the waveguide? Now, when we say the cutoff frequency, one thing that might be in mind is cutoff frequency of which mode? There's a whole bunch of modes, and they each have their own cutoff frequency. So normally when we just say the cutoff frequency, what is meant is the cutoff frequency of the absolute lowest order mode. And so below that, no modes would be supported. Well, we know that cutoff frequency, and given these dimensions, we calculate that to be 5 gigahertz. So if we tried to use this waveguide at 4.9 gigahertz, we just could not squeeze that wave into the waveguide. Our frequency has to be 5 gigahertz or higher in order for that waveguide to support a mode. Next question, over what range of frequencies is the waveguide single mode? Well, we've calculated the lower number, but what's the upper number where the next order mode suddenly pops into existence? And that would be our range of frequencies. Well, in this case, A is not greater than 2B. So the second order mode in this case is the TE01, not the TE20. So we'll plug in our equation for the TE01 mode, and we get 7.5 gigahertz. So our final answer is this waveguide is single mode from 5 to 7.5 gigahertz. Below 5 gigahertz, no modes exist. Above 7.5 gigahertz, we have at least 2 modes that would be supported by that waveguide. What's the fractional bandwidth of this waveguide? Well, we know the bandwidth, we just calculated it. We can divide by the center frequency, and in this case, the way I'm calculating the center frequency is that I'm averaging the upper and lower frequency. And when I divide by 2, that 2 comes up here and our 100% becomes 200%. So we throw in our numbers and we get 40%. So by making A less than 2B, we've hurt the bandwidth. And this is actually the reason that rectangular waveguides are so rectangular, because that's how we maximize the bandwidth of the waveguide. So let's plot the phase constant and effective refractive index for the first and second order modes all the way from DC up to 15 gigahertz. So we need some equations to do that. So we have our phase constant, and if we plug in 1 and 0 for M and N, here's the phase constant we get. If we plug in 0, 1 for M and N, we get a second phase constant. And so we want to plot these as a function of frequency. The effective refractive index, it's really just our phase constant divided by this K0 term. So once we calculate our beta, we divide by K0, and then we'll get our effective refractive index. Okay, given those equations, I've summarized the equations that we derived up here, and down below we're plotting it. The plot on the left is the phase constant, and the plot on the right is the effective refractive index. Let's look first at the phase constant. Remember, the low order cutoff frequency was 5 gigahertz. That's why below that we don't see any beta. It starts here at 5 gigahertz, and from there it increases. And it has a little elbow region, but at some point it just becomes a straight line. And getting a little bit advanced here in a side topic, we're looking at this curvature here, and that really means that the waveguide is very dispersive. If we have a signal occupying this bandwidth, each of those frequencies are going to be traveling at a different speed. We really want to operate above that low order frequency where this line becomes straight. And that's where they're all going to have the same effective refractive index. So we tend not to want to operate right near a cutoff. The second order mode does not exist until 7.5 gigahertz, and then it also increases linearly. And so we can plot the effective refractive index. Notice this is always less than 1. That's telling us that these modes in the waveguide must be traveling faster than the speed of light. Does that bother you? Well, let's plot the velocity as a function of frequency, which of course just comes directly from the effective refractive index. So we take the speed of light, divide by our effective refractive index, and we have the velocities. So here's what they look like. Notice right at cutoff, our velocity is huge. It actually approaches infinity. Certainly right above that, we have some very fast propagation, but then it sort of converges to 1, and we go way up high. So way out here at super high frequencies, the mode in the waveguide is traveling immediately at the speed of light. But realistically, if we're operating this as a single-moded guide, we're operating right here. And the mode actually seems to be traveling faster than the speed of light. So I'll ask it again, does that bother anybody? What's going on here?
Visualization of the TE modes. It makes sense to start with the lowest order mode, and for the TE modes, that's the TE01 mode. So we have the XY cross-section. That's the cross-section of a waveguide, the two-dimensional picture of the fields that we calculate. That'll be in the XY plane. And then we can see the mode propagate in the Z direction through the waveguide. And in this case, we're just looking at the Z component of the magnetic field. So you have to realize there's more to this mode. We're just visualizing that Z component. So this is the TE01 mode. And let's think about interpreting these subscripts. The first number is how many bright spots in the X direction, and the 1 is how many bright spots in the Y direction. So let's think about that. If we look at the X direction, and it's even more clear to look at if we just look at this cross-sectional picture, but we can also get it by looking at the guided mode as well. It's completely uniform in the X direction. There's not like it ends or anything on either side, like there was a cosine hump or something. And so that's 0 bright spots then. Whereas in the vertical direction, there's 1 bright spot. And you might be looking and say, hey, it looks like there's 2 bright spots. They're just 180 degrees out of phase. And maybe this aspect is a little bit easier to see when we're looking at the guided modes. But what you see is the top bright spot is really just half of a bright spot. So you're looking at half of a sine wave right here, and then you're looking at another half here. So if we add the 2 halves, we do have 1 bright spot. And as I mentioned, I think it's easier to see in the actual animated guided mode than in the cross section. Let's go on to the next mode. So the next order mode is the TE10. And we're looking at essentially the same thing here. We're looking at our propagated mode. We're looking at the Z component of the magnetic field. and we need to understand there's more to this. But let's think about the subscripts. There should be one bright spot in the x direction and 0 bright spots in the y direction. Well, in the y direction, we see the field is completely uniform. There's no cosine or sine humps, so that counts as 0 bright spots. In the x direction, there should be one bright spot, and it kind of looks mysteriously as if there's 2 bright spots, but 180 degrees out of phase. And again, this is a little bit easier to see in the animated guided mode, but what you're actually looking at is 2 half bright spots. So overall, it's 1 bright spot. And the next mode is the TE11. So this should give us 1 bright spot in X, 1 bright spot in Y. And that's exactly what we see. And I think it's maybe a little bit more obvious in this picture that we're really looking at half bright spots here. And so if we look in the X direction, we have 2 half bright spots. In the Y direction, 2 half bright spots. So overall, that's 1 bright spot in each direction. TE11. Next mode, the TE02. We should be seeing 0 bright spots in the X direction, 2 in the Y direction. So yes, a nice uniform field in the X direction, that's 0 bright spots. And then in the vertical direction, the blue is a full bright spot, and the 2 greens here, that's a half bright spot each. So overall, we have 2 bright spots in the Y direction then. TE20 mode. 2 bright spots in X, 0 bright spots in Y. And we definitely see 0 bright spots in Y. It's perfectly uniform. We don't see any sine or cosine humps here. But in the X direction, we see this blue region here as a full bright spot, whereas the green is 2 half bright spots. So in total, 2 bright spots in the X direction. TE12. We should have 1 bright spot in the X direction, 2 in the Y. So in the X direction, yes, we see 2 half bright spots. Then in the vertical direction, there's 1 bright spot and then 2 half bright spots. So overall, 2 bright spots in the vertical or Y direction. TE21 should be 2 bright spots along X and 1 bright spot along Y. So let's go along X. Yes, 1 full bright spot in the middle and 2 half bright spots on either side. So in total, 2 bright spots in the X direction. In the Y direction, we see 2 half bright spots. So in total, that's 1 bright spot in the Y direction. We'll look at some more modes, but rather than look at the Z component of the magnetic field, here we're looking at the vector XY components of the electric field. And here we can tell, for example, this mode, the TE10, it's very linearly polarized in this vertical direction. TE20 mode, when we're looking at electric fields, it's easier, I think, to count the bright spots because we're always looking at full bright spots. Whereas looking at magnetic fields, we get these half bright spots on either side. That's just due to having different boundary conditions. Again, looking at this is a very linearly polarized mode. TE01, this is still linearly polarized. Now it's linearly polarized in the X direction. 0 bright spots in the X direction because there's a uniform field, 1 bright spot vertically. TE11. This is starting to look kind of pretty. Now, this is not a linearly polarized mode. We can see some curling here, so not all modes are linearly polarized. But if we were interested in those lower order ones or the first few we looked at that were linearly polarized, making that kind of approximation in the analysis, that becomes an approximation, but it can certainly simplify things. So always be looking for that. TE21. The higher order modes, they become less practical, but I think they look prettier. Conclusion.
So here's a summary of having done the TE analysis of a square waveguide. We have our field solutions on the left, we have our phase constant, our cutoff frequencies, and our characteristic impedance. And the equations, as it turns out, for the phase constant and the cutoff frequency, they're actually the same for the TE and TM modes. We will derive them for the TM mode, but we get the same equations. That's convenient because when we calculate them, it counts for both. We don't have to do more calculations. We'll conclude that the TE00 mode does not exist. So for TE modes, when M and N are both 0, that's not counted. Now M and N can be 0, but not at the same time. We also found that the TE10 is the lowest order TE mode.
From the bottom of my heart, thank you so much for using EMPossible. I want to create more videos, and I want to continue to improve how electromagnetics and computation is taught online. To do that, it will really help me if you can like this video and subscribe to our channel. I also want you to know we have a lot more content that you may not be aware of. See everything we have to offer at EMPossible.net.